Welcome to Mrs. Z's Chemistry. This is 14.5, where we talk about weak bases. If you haven't already watched 14.4, weak acids, you might want to do that for more context. Alright, so bases react with water. They accept a hydrogen ion from water, and then they produce hydroxide. So you can see this is the base, ammonia, NH3, and it's going to accept a hydrogen ion from water. Then the NH3 turns into NH4 with a positive charge because it's a hydrogen ion, and the water is left looking like this, hydroxide minus. So here is, again, the reaction, but now B is just representing any weak base. When it accepts a hydrogen from the water, it looks like this, hydrogen, or HB with a positive charge, and then the hydroxide is OH minus. The Kb, or base dissociation constant, looks like this here, where we have the products, the Hb and the OH, the concentration. Remember that when we have brackets around the compound, that is the concentration in molarity of the substance, divided by the reactants. And also remember that liquids and solids are not included in the Kb or Ka or any K expression, only aqueous substances. If we had gases in the reaction, you could also include gases. So only aqueous and gases, not liquids or solids. Here's a list of some weak bases. Of course, this is not an exhaustive list, but here's just some of them. So let's look at ammonia, again, NH3. Here's its Lewis structure. Once it gains a hydrogen ion, it now looks like this, NH4+. Here's the reaction where water is transferring a hydrogen ion to NH3, and these are the products left over. When we calculate the Kb at equilibrium, then we have 1.8 times 10 to the negative 5. Notice that all of these K values are less than 1. That is because all of these reactions are reactant-favored reactions, meaning the reactants barely turn into products. The majority of the reactants stay as reactants, and there's not very many products in the solution. Remember that when we have this double arrow, that means this is a reversible reaction or an equilibrium reaction, and all four of these substances are together in the beaker or in the container. And because the Kb is very small, that means we had a lot of reactants in the solution at equilibrium and very little products. All right, so these are the equations on your periodic table. Kb is equal to x squared over b minus x, where x is equal to hydroxide. It's also equal to the conjugate acid, which has this form. It's the base after it has gained a hydrogen ion, but we normally don't solve for the conjugate acid. So x is equal to hydroxide, and the value of x, or the value of hydroxide, is squared in the numerator, and then the lowercase b is equal to the concentration of the weak base, and this is given in the problem, and it's usually written as originally or initially, or just the concentration of the weak base is, and that's what you plug in for b. Now, since most of these weak bases separate less than 5%, x is so small that b minus x is still equal to b. So this means we get to ignore the x in the denominator. You can just ignore it when we are solving for x. So let's try this example problem. What is the pH of a 0.15 molarity solution of NH3? Here's the reaction. NH3 is the base, accepts a hydrogen from the water molecule, leaving this as the products. The Kb is the products over the reactants. Again, leaving out the liquid water. I should have our little states of matter in here where everything else is aqueous or AQ. The Kb has this value. Our general equation for Kb is x squared over b minus x. So let's plug in the values that we have. 1.8 times 10 to the negative 5 is the Kb. X squared, b is this, 0.15. Now, if we did not ignore the x in the denominator, we would have to use the quadratic equation in order to solve this. But in Honors Chem, as well as even on the AP Chem exam, we are not expected to use the quadratic equation, and this is because x is so small that 0.15 minus x is still just 0.15 when you round it to two significant figures. And since 0.15 represents a measured value that was used with a graduated cylinder that could only measure to the tenths or hundredths place here, it doesn't make sense to have a very small number that's very close to 0.15 but doesn't quite round to it, or that does round to it. So we just keep 0.15, we ignore the x in the denominator, and now we can solve this with simple algebra. Solve for x. So when you solve for x, we get 1.64 times 10 to the negative 3. X, if you remember, equals hydroxide, because we have hydroxide in our reaction. We don't have H3O in the reaction. H3O, by the way, is actually in the solution, but it's not in the chemical reaction here. So X is equal to hydroxide. So when we take the negative log of this, we would get POH, and then you would have to convert that to pH. Pause to see if you can solve this. So when we take the negative log of our X value, that's hydroxide, so this is POH, and then so turn that into pH, and we get 11.22. All right, pause to see if you can solve this problem. Here is the answer. All right, let's do a few more review problems. If you have a 0.014 molarity HCl solution, see if you can solve for the H3O, the OH, the pH, and the POH. Here are all of the answers. HCl is a strong acid. Therefore, the concentration of the strong acid, which is the 0.014, is also equal to the concentration of H3O. So that's an easy problem. Use the KW equation to convert H3O to OH, and here's the OH concentration. Take the negative log of the H3O, and that gets us pH. Subtract from 14, and the pH turns into POH. Try this again, but now you have 0.025 molarity NaOH. And here are all the answers. NaOH is a strong base, therefore the strong base concentration is equal to the hydroxide ion concentration. A weak acid has a Ka of 1.7 times 10 to the negative 7. What is the pH of 0.15 molarity solution of this weak acid? Remember that Ka, which is given here as this value, has the general reaction of x squared over A minus x, where x is equal to H3O, and A is equal to the concentration of the weak acid, which in this problem is given as 0.15 molarity. The problem is asking for pH, so once you find x, plug it into this equation. Pause to see if you can work this problem out. Then, what if you have a solution? What is the pH of the solution if you have a 4.75 molarity solution? So it's the same weak acid, but we just have a much stronger concentration. Exchange the A now for 4.75, and everything else is the same. All right, so here are the answers. For the original solution of 0.15, we have a pH of 3.8, but when the concentration is much stronger or much higher concentration, we have 4.75 molarity, then the pH is a little bit more acidic at 3.05. A weak base has a pH of 10.78. What is the Kb of a 0.26 molarity solution of this weak base? Kb has the general reaction of x squared over B minus x, where x is now equal to hydroxide. And the B is equal to the concentration of the weak base, which in this problem is this. Now we're trying to solve for the Kb, and we were given the pH as 10.78. Pause to see if you can solve this problem. Then, what is the percent ionization of this base? Percent ionization of a base is going to have the hydroxide over the concentration of the weak base, which in this case is the 0.026, because it's all the same solution, times 100, and that's equal to percent ionization. Pause to see if you can work this problem. And here are your answers. The Kb of the weak base is 1.4 times 10 to the negative 6, and then you take your hydroxide value and use that in the second part, and we get 0.23%, less than 1% that this base ionized. So the stronger the acid, the weaker the conjugate base. And this is because a strong acid very readily loses the hydrogen ion. Therefore, if it very readily loses the hydrogen ion, its conjugate base is not going to accept that hydrogen very well. And the other way around, a very weak acid has a very strong conjugate base. Remember that the acid is represented as HA. When it loses its hydrogen, it looks like A minus. So here's the acid and here's the conjugate base. If the acid is weak and therefore has a very strong attraction to its hydrogen, the conjugate base of this acid is going to be a very strong base. It's going to accept that hydrogen very readily. The same is true for bases. The stronger the base, the weaker the conjugate acid. The Ka and Kb of an acid and its conjugate base, or of a base and its conjugate acid, equals Kw when you multiply them together. So we have this reaction or chemical or equation on our periodic table where Kw is equal to the H3O and OH multiplied together. Well, it's also equal to the Ka and the Kb of an acid and its conjugate base. So let's try this. Use the Ka for HF, which is 6.8 times 10 to the negative 4, to find the Kb for its conjugate base, which is F minus. If you plug this into this equation here, you should get the answer. Pause to see if you can work this out. So Kw divided by Ka equals the Kb. This is the Ka for HF. Let's use the real acid here. And then this is the Kb for the conjugate base of F minus.